not breaking the OH bonds. Right? We're just breaking the hydrogen bond. Okay, so here's a question. Which has the higher boiling point and melting points? Ethanol or dimethyl ether? To be sure, we have to draw it. So if I do ethanol, okay, here's my ethanol molecule versus here's dimethyl ether. Oh man, that takes too much time to draw. Alright, so these are the two molecules. If I did the line structures for them, that'd be a line structure, and this would be a line structure. That's so much easier. Anyhow, so which one is more polar? Or more likely to have a higher melting point? Yeah, the ethanol or the ether, definitely the ethanol. All right, why is that? Right, it's got the OH bond in there now. So now it's capable of doing what water does, right? Having these OH attractions. This molecule here has oxygen in the center, but it does not have a hydrogen directly bonded to it. And that's the key idea. Okay. So these hydrogens attached to the carbon don't count. So while this one can do dipole-dipole forces, this one can do dipole-dipole and also H bonding. All right, so I could have another methanol or ethanol molecule so you could have an H bond like that right there. Whereas like with this guy, okay, I would have to line up the dipoles. I'd have to line up the dipole moments that way. All right, this guy would have to come way down here. Okay, now I can sniff you from the rear end. This one's like, oh, I don't have to sniff you from the rear end. I just do the glance. Okay. Let's check you out from the side glance. All right. And it turns out that the boiling points are affected. So they both have the same molar mass, but check this out. Minus 22 for ethane, 78 for ethanol. Alright, so at minus 22, you know that dimethyl ether is going to be a gas, but ethanol is going to be a liquid at room temp. Here's another cool application of this. When I was in industry, we had to develop gas chromatography methods for doing blood alcohol content. So when someone gets busted for DUI, they get pulled over, right? They do the breathalyzer in the field, but then they take them, if they don't pass the breathalyzer, they haul them to prison, they get a warrant to draw your blood, they draw your blood, they put it in an ampule, a gas-tight vial, take your blood, they boil it to right about, or they heat it up to right about the temperature to which ethanol starts to boil out. Okay, you're mainly aqueous, so the water and the proteins and all the blood cells stay behind, but all that ethanol vapor comes out. And then they take a gas-type syringe, they pull out the gas, the vapor of the ethanol, and they inject it into this machine so you can calibrate it for ethanol. And that's how they can tell for sure if you're above the legal limit for driving an influence. So they say, well, I'm going to fight it in court. Will you now? Breathalyzer, guilty. Gas chromatography analysis, guilty. Two different methods, right? So can you really fight that one? I don't know. It's a long shot. Unless you call no cuts, or 1-800-NO-CUTS, right? Unless you're into that sort of thing. Anyway. I love that commercial. Anyway. Have you ever heard the commercial before? 1-800-NO-CUTS? Anyway. Okay. Yeah, just look it up, it's funny. The guy's even funnier, like he looks weird. You know? So given these three different forces we talked about, how do you determine the kinds of physical properties? Like how do you compare boiling points and melting points? First step is you got to determine the kinds of intermolecular forces, which requires you to draw the Lewis structure and perhaps even the shape to determine if it's polar or not. So notice how, like with water, with ethanol versus ether, I drew those Lewis structures, and I kind of drew them somewhat in the shapes, you know, of the molecules. This is bent right here, right? So I'm like, well, okay, ether's got dipole forces, but ethanol has hydrogen bonding, which is even stronger, right? So from that we said ethanol has the higher boiling point. So you got to draw the structures, compare the intermolecular forces based on strength, and then evaluate the strengths. So here's one more. So you got formaldehyde, fluoromethane, hydrogen peroxide. Which one of the following is a liquid at room temperature and why? So that insinuates the others are probably gases. So what would we first have to do? Right, so you have to draw the Lewis structure. So what's the Lewis structure for formaldehyde? So here's the Lewis structure. That's the Lewis structure. The Vesper sketch, though, is going to be that, right? So you got Lewis, Vesper, right, and then you have the other one. Here's fluoromethane. What's that going to look like? All right, there's the Lewis structure for fluoromethane. And then for HOOH, right, there's the structure for the last one. What would be the Vesper sketch? What would that be for this? This is a tetrahedral carbon, right? So it's really going to be fluorine, we're all pros at drawing tetrahedral compounds now, right? If not, we will be. We're going to do more of this today. So, and then we have our HOOH. How would I draw the shape for that? What's the shape around this inner oxygen? It's going to be bent. So I could do it that way. Or I could do it this way. Okay, but we'll keep it this way. All right, so which one has the greater dipole moment? Well, actually, let's go through these. Do they have, which one has the higher molar mass? Well, they all have the same molar mass, really. So dispersion forces are about the same. What about dipole-dipole forces? Are any one of them not going to be dipole-dipole? They all have dipole-dipole forces, right? This is asymmetrical, right? The dipole moment points up. Here's another dipole-dipole force. Here's another dipole-dipole force. So the dipole moment might be a little bit different, okay, but they all have dipole-dipole forces. What about H bonding? Do all of them hydrogen bond, or is only one of them? The one on the right, the hydrogen peroxide? So this one has H bonding capability. Right, this one has OH bonds in it, right? This one does not have OH. It doesn't even have FH, right? The F is here, but the H's are only attached to the carbon. Right? This has O in it, but again, the H's are attached to the carbon, not to the oxygen. So because of that, the molecule on the right is the only one that can H bond. And therefore, it would have the higher boiling point because it can hydrogen bond where the others can't. What do I mean when I say, oh, it can hydrogen bond? What am I talking about? What am I talking about? What I'm talking about is, if it came into contact with another HOOH molecule, it can H bond with itself, or with another molecule just like it. All right, I could have another HOOH attracting here, right, for example. So the winner is hydrogen peroxide, because it can H bond.
So I have a question. So in structure, the fluorine, nitrogen, or oxygen has to be bonded to a hydrogen.
It must be bonded to a hydrogen, right? So the NO or F has to have an H bonded to it directly. If it doesn't have that direct bond, then it cannot hydrogen bond. Yeah. So NO or F must have H on it. Right? FH, OH, or NH bonds. And FH, probably the least common. Usually you're looking at OH or NH bonds. Here's a real quick knowledge question. Which one of each pair will have a higher boiling point? Explain why. So really, we could do all the structures, go through the process, but can you tell just by looking at it? And this is what you should try to get to. Can this hydrogen bond? And the answer is yes. This H is directly bonded to that O. Can this hydrogen bond? Is this H bonded to the fluorine? And the answer is no. Okay, this H, last time I checked, we cannot have H as an inner atom. It has to be an outer atom. If this was an outer atom, the H would actually be over here, written as if it were attached to the fluorine, just like this is written as if it's attached to the oxygen. So what this is here is you got carbon bonded to that carbon, bonded to this hydrogen, and then the two fluorines are also bonded to the carbon. So it's actually, that's the framework for that molecule on the right. So there's no way that hydrogen's on the fluorines, and therefore you don't have hydrogen bonding. Right? Whereas with methanol, right, here's methanol. The H is actually on the oxygen. So the winner for those two would be what? CH3OH, right? So that can H bond, the other one can't. What about the other pair? Does this win or does that win? This guy, right? The O is between the two carbons. Remember when they, going back to condensed structures, I mentioned this yesterday, the CH3 means H is coming out from that carbon, not bonded to that. Right, so yeah, this has the hydrogen bonded directly to the nitrogen. So that's going to be capable of H bonding. All right, so the solubility is also affected. We're going to run out of time here. Real quick, I want to point out something. In your supplemental learning packet that I gave you a long time ago, you have this page listing the forces that that we've been talking about. So I think it's the very last page. So just use it. You can use it to study and also use it for problem solving. So this is a nice summary of the forces. And it starts from dispersion forces at the bottom, and if you work your way up, you're going to increasingly stronger forces. So, just a summary of what we've been talking about. So next time we'll have to do, we'll do dipole, ion dipole, and then we'll do